This video is about the mean value theorem. And before we get to the mean value theorem, we're going to talk about another theorem called Rolle's theorem. And also, I just want to mention that the mean here is mathematical mean, like average. So it's important to remember that when you're sort of trying to recall what the mean value theorem means. You might also consider this like the average value theorem. So Rolle's theorem is a sort of special case of the mean value theorem. So let's see what it says. Assume that f is continuous on some closed interval a to b, and it's differentiable on the open interval from a to b, okay, meaning you can take its derivative everywhere on this interval. If the y values of the endpoints are the same, f of a equals f of b, then there's a number c somewhere in here, right? This symbol just means that it lives inside this interval, such that the derivative at c is equal to 0. Okay, so basically what that says is, like here I've got two different curves so that we can sort of see what's going on. If I take this blue curve, you can see that the f of a and f of b, they're supposed to be the same here, right? They're at the same height. So if these are the same, then there's supposed to be a point somewhere in between these 2 points where the derivative is equal to 0. And in this case, there are several, right? I mean, like there's this one, there's this one, there's this one. Or similarly, if I look at the purple curve, right, like here the y values are the same, so there's supposed to be a point somewhere in between these two where the derivative is 0, and there is. So again, there might be one, there might be many. All this says is there's definitely one. And the reason that this works is, if you imagine, so it's continuous and differentiable, which means that basically, so continuous meaning like you're not allowed to skip any values, right? Like if this thing goes down, it eventually has to come back up, right? Because it starts and ends in the same place. So if I go down, well, at some point I have to turn back up. And when I do, I know that I'm creating a sort of a place where the tangent line is going to be horizontal, right? If I'm going down and then I have to come back up, that creates a horizontal tangent line spot. And because it's differentiable, I know I don't have like a sharp point. So remember, not differentiable, things like that are not differentiable, but I'm disallowing that. So not only am I going to sort of create the bottom of a valley if I start by going down, but when I come back up, I'm going to do it by remaining differentiable, right? And when I do, I'll create this type of place that has a horizontal tangent line, or in other words, where the derivative is 0. So the Rolle's theorem is a special case of the mean value theorem. Okay, so let's check out the mean value theorem. The mean value theorem starts out all the same way. So you assume that your function is continuous on a closed interval and differentiable on an open interval, except now we're not insisting that the endpoints match. So the first sentence here is the same for these hypotheses, but on Rolle's theorem we assume that they have the same height at the end, but now we don't have that assumption. And then if you skip over that assumption, we get there's a point C in the interval such that something. But in this case, it's not going to be the derivative is equal to 0. Okay, it's going to be the derivative is equal to something else. So let's see if we can think about what it should be. So in Rolle's theorem, we had the same height, right? And so if I went down, I was going to have to come back up, right? Or if I went up, I was going to have to come back down, which was going to create that place where the derivative was equal to 0. Now, if they're not the same height, I don't create a place like that. So here's where the average in mean value theorem occurs. If you want to think about like the average of every single tangent line, the slope of every single tangent line in here, some of them are going to be pretty negative, right? And then you've got some that are positive and some more that are negative and some more that are positive. But if you wanted to average the slope of every single tangent line in here, what you would essentially get is the slope of this line, right? If I take what's called the secant line between these 2 points, the slope of this line is sort of the average of every single slope of all the infinitely many tangent lines in here. So if I go back up to Rolle's theorem, when I get that the derivative is equal to 0, I get that because the line between these two has slope 0, right? The line between these two has slope 0. That's what we get by insisting the y values here match. But when I don't make them match, instead of getting the derivative is equal to 0, instead I should get the derivative is equal to the slope of this line. So you may or may not remember formula for slope when you have 2 points, but it's going to be f of b minus f of a over b minus a. right? Difference in y's over difference in x's, rise over run. So this is what the mean value theorem says. As long as your function is continuous and differentiable, then there has to be some point in the middle that sort of matches the average slope, where average slope is the slope of the secant line. Okay, so let's see what this might look like in a problem. Show that the mean value theorem holds for the function square root of x on the interval 1 to 9. So the first thing we have to do is verify that this thing meets the hypotheses. So is this continuous on the closed interval from 1 to 9, and is it differentiable on the open interval from 1 to 9? Right, because we have to know that both those things are true before we even start talking about the conclusion of the mean value theorem. But, I mean, if you can think very briefly about what the graph of square root of x looks like, it is going to be continuous on this interval. It is going to be differentiable on this interval. Okay, so then, to show that it holds, we need to find the point in here that hits the average slope. So we might start by asking, what is the average slope? Right? Or in general, what's the slope of that secant line through the endpoints? Right? It's going to be f of 9 minus f of 1 over 9 minus 1, right? Using our formula from the mean value theorem. So if I plug in f of 9, right, I get square root 9 minus square root 1 over 9 minus 1, or 3 minus 1 over 8, or 2 over 8, or 1/4. So this is the average of all the tangent lines, the average slope for all the tangent lines in this interval. So what I need to do is find a point in here, right, in the interval from 1 to 9. So I need C in the open interval from 1 to 9 such that f prime of C equals 1/4. Because that's what the mean value theorem says, is there is one of these things, right? There's something between 1 and 9 where the derivative is equal to 1/4. So to find this, I'm going to take the derivative of the function f prime of x, right? And that's going to be 1/2 x to the negative 1/2, right? Just using the power rule. I'm going to take that 1/2 x to the negative 1/2, and I want to find out where is this equal to 1/4. Because, right, the first derivative is what gives me slopes of tangent lines. So here I've taken the derivative of square root x. I want to know what's the x value that makes this true. So now I'm just going to solve this, right? I multiply both sides by 2 and get x to the negative 1/2 is equal to 1/2, right? And then I can sort of rewrite this. If I have x to the negative 1/2, that's sort of like 1 over square root x is equal to 1 over 2. But that is going to imply that square root of x is equal to 2, right? So I can use like the sort of reciprocal property here. And then I can square that square root away and just get that x is equal to 4. And 4 is, in fact, in the interval from 1 to 9. Check. So in this case, x equals 4 is the point that satisfies the conclusion. So again, if I sort of go back up here, I showed that I sort of observed that my function was continuous and differentiable, and then I found the point 4 in 1 to 9 such that the derivative at 4 matches the average slope. Okay, so that's just sort of verifying that the mean value theorem works. The other thing you can use Rolle's theorem or the mean value theorem for is to talk about the number of roots that an expression has. You can also use it to verify identities and things, but let's just do one of these. So how could I use these results to show that this function has at most one real root? So this may not obviously look like a mean value theorem or a Rolle's theorem problem, but we can use it here. So this is asking us to show something, so we're just going to work out the proof here. And we're going to use a very common proof technique called proof by contradiction, which is I'm going to assume the opposite of what I'm trying to show. So I'm trying to show there's at most one real root, so I'm going to assume, for the sake of contradiction, that there are at least 2 real roots. Let's call them A and B. Those are my 2 roots. And so the idea in proof by contradiction is I'm going to assume something that's sort of like the wrong thing, and I'm going to end up somewhere that's fantasy land. So if I assume this and I get something that doesn't make sense, then I know that, oh, this must have been wrong, and I'll have what I want. So I assume there's 2 real roots at A and B. Well, so what is a root of a function? That means that f of a is equal to 0 and f of b is equal to 0, right? So by Rolle's theorem, what are we going to know by Rolle's theorem? You might want to pause and ask yourself. We know there is a c specifically in between -2 and 2 because a and b are both in there as well. We know that c really lives between a and b, but we don't know where a and b live in this interval. So there's a c somewhere in here such that f prime of c equals 0, right? So in particular, I'm assuming that these two roots a and b, these are in this interval in question, right? So I assume there's 2 that live in here. Well, if they're roots, then they have the same y value at 0. So by Rolle's theorem, there's something between them, and hence in this interval, such that the derivative at that place is 0. But if I take the derivative, all right, so if I go back up and see, the derivative here is 3x squared plus 15. Okay, so I'm trying to find c such that the derivative is 0. Well, where is the derivative 0? I take this and set it equal to 0. And I end up with 3x squared 3x squared equals -15, or x squared equals -5. That doesn't make any sense, right? I mean, if I square something, I'm never going to end up with something negative, right? So here, I'm trying to show there's at most one real root in here, so I assume there's 2, which tells me that there ought to be a place where the derivative is 0, but it turns out that this derivative is actually never 0. So this would be true even if I didn't have this -2 to 2 slapped on here, right? I mean, there's no way that there are 2 real roots to this function at all, because when I take the derivative, there's no place where the derivative is equal to 0. So this is a contradiction. So when you're doing proof by contradiction, when you get to your contradiction, you go back and flip your most recent assumption. And the only thing I assumed here at all was that there were at least 2 real roots. So the opposite of at most 2, or rather at least 2, is at most 1. So thus, there is at most 1 real root of f. And in fact, this is true just in general, but if you want to be specific about what the problem was asking us, there's at most 1 real root in this interval from -2 to 2. Right? So now we got what we wanted. So you can use the mean value theorem or Rolle's theorem to do this sort of proving things in situations where it doesn't exactly look like you might need it. But usually for a standard calculus student, this is more like the type of problem you're going to be expected to work, is to sort of verify the conditions of the mean value theorem for some function on a specific interval. All right. So let's just remind ourselves, the mean value theorem, that's the average value theorem, and basically what it says is if you've got something that's continuous and smooth, right, continuous and differentiable, then there has to be a point somewhere in the middle that matches the average slope of all those tangent lines. So you can imagine sort of sliding this line down, right, and there's going to be several places, in fact, here that sort of hit that average slope. So all of these places are going to sort of have the correct slope here.